Thank you for joining us today. I'm pleased to be here with Rob Travis from Cascade Energy, who will be talking about optimizing condenser performance for industrial refrigeration systems. Rob, would you move to the next slide, please? I'd like to take a moment to thank our 7th Wave members for making today's presentation possible. We are deeply grateful for their support of our online education. And now I'll turn it over to you, Rob.
Thank you. Today we're going to talk about 4 low-cost condenser action items to improve condenser performance in industrial refrigeration systems. The first one we'll talk about is reducing condensing pressure. We'll move on to enabling wet bulb approach, talk about proper condenser sequencing, and then optimizing our condenser performance. The first one, reducing condensing pressure. This is something that energy consultants are always banging the drum on in order to achieve the most energy savings in a system. And it's true. You can get about 1.5% compressor savings per degree Fahrenheit reduction by reducing your condensing pressure set point. However, it's not as easy said as done. Reducing our minimum condensing pressure set point, we need to eliminate the barriers to the minimum allowable pressure. And then we also need to take a look at the condenser approach, and that's the approach of pressure to the wet bulb temperature. Important to note that reducing approach and minimum pressure are completely separate issues, not to be confused or overlapped, and we'll go into both issues in the next few slides. So targeting the minimum condensing pressure, in this example we have right here, is a system that was operating with a fixed pressure with the green line throughout the year. So the graph shows the condensing pressure from January through December on the green line, and you can see it's at about 78 degrees all year round. On the blue line, this is our average wet bulb temperature throughout the year, and as you can see, the wet bulb temperature is going to increase through the summer months as we'd expect. Now, if we're able to reduce our condensing pressure set point from the green line down to the red line, which is going to be right around 58 degrees, somewhere around 90 pounds with an ammonia system, the shaded blue line is the savings that we're going to achieve, and the savings is going to be directly related to our compressor savings. Note that we're reducing the condensing pressure set point to achieve savings on our compressors, which are going to be the largest energy consuming system in the refrigeration system. So throughout the year, we can see the savings are not going to be consistent. We're going to achieve more savings in the colder months during the winter, the fall, the spring, the shoulder months, and probably very little savings in the summer months. But that's okay. We're going to achieve savings where we can, and in this case, it's going to be in the off-season. Also important to note is that most refrigeration systems can operate with a target set point of between 90 to 110 pounds. Now, each system has to be evaluated independently because there's different barriers each system has to get into that minimum condensing pressure set point. So how often can we achieve such a low condensing pressure? Well, looking at this example, this is a typical weather for Madison, Wisconsin. And you can see that with a 12-degree approach to wet bulb, over on the left-hand side of the chart there, about a full 55% of the year, this system would be able to operate at a 90-pound set point. So the system will be able to operate at this lower pressure for the great majority of the year. At 100 pounds, it's only going to be about 5 to 7% of the year. And you can see as it increases up to 150, 160 pounds, a very small fraction of the year will it actually be operating at that higher pressure, with the largest majority of the time being able to operate this lower, more efficient pressure. So how do we get to that point? Well, your condensing pressure is set to what it is for some particular reason, and what you need to do is identify what that reason is. Is it something where it was set up by the contractor? Is it just because it's been there forever and that's just the way we do it? Or is there a limiting device in the system? So we've got a lot of things to look at in this slide here, and I'm not going to go over them in great detail, but each one of these needs to be evaluated by you and your team as you look at being able to reduce the condensing pressure set point. And the idea you can see over on the right-hand side is that we want to find out what these barriers are, and as we come across a barrier, see if we can address it and find a workaround to get past it. So in this case here in the example, we've got the minimum condensing pressure set point. As we start reducing that pressure, we may find out that liquid injection in our compressors becomes an issue. Well, is that something that can be overcome? Can we retrofit that to a thermosiphon system? Can we retrofit that to motorized liquid injection valves that have a lower pressure differential? If we can do our capital project to change that out, then we can start reducing our condensing pressure some more. Maybe we come across some hot gas defrost issues. With those, we may have one or two coils that aren't getting proper defrost. Well, maybe the defrost line isn't big enough. Maybe those coils have some bad valves, but those need to be addressed. And as they are, then we can start reducing our pressure some more. And by this sequential approach, you'll keep on coming across a barrier, try to overcome the barrier until you reach something, and in this case you can see the oil separator on the compressor, you'll reach something that is not overcomable. And with that, that becomes your low condensing pressure set point. So the different things you need to be able to look at, the list right here just very briefly: hot gas defrost, making sure we get adequate defrost in our coils; heated zones, if you need to be able to provide heat to any of the heated rooms; icing or other winter issues; water defrost in a common sump; oil separator performance on your compressors; if you have any gas-powered valves that require a higher pressure; if you have any unloaders on your reciprocating compressors; liquid injection oil cooling that have the older style thermostatic expansion valves that require a higher pressure differential; screw compressor oil carryover; underfloor heating requirements; pumper drum operation; direct expansion coils; process or hot doors that require hot gas for heating; inadequate liquid pressure to serve loads, not be able to get the liquid refrigerant out into the facility; concerns about condenser, fan, and pump energy, worrying about any energy savings we see on the compressor might be eaten away by the additional energy required by the condenser fans and pumps; misperceptions about volume ratio and efficiency, and just typical tradition. So the point being that these are all very real barriers, and they all have to be addressed to make sure that they can be overcome as you reduce your minimum condensing pressure. Moving on to the next portion here is enabling wet bulb approach. So wet bulb approach is a condensing strategy that strikes an effective balance between compressor power and condenser fan and pump power. So it ensures the excessive condenser power is not used to try to achieve an impossible condensing pressure based on a high wet bulb temperature. So in the condition where the wet bulb temperature is much higher than normal, and we're trying to get a 90-pound set point where our condenser fans and condenser pumps are operating full speed, trying to get to a lower condensing pressure that's just physically not possible, using this condensing wet bulb approach strategy will allow those condenser fans and pumps to back off. This is particularly beneficial if you have VFDs on those fans, where it can start reducing the fan speed from, say, 100% to 90% or 80%. And that's not really going to change our condensing pressure at that point in time. So our compressor power is going to be the same, but we're going to save a little bit on the condenser side. So this is really a way to strike a good balance between our compressor and our condenser power. Typical approach values when you set that up is setting an approach about 12 degrees to 18 degrees. And that approach is the difference between our wet bulb temperature and our condensing temperature and its related pressure. The last point I want to make here is there's an incremental economic return with larger condensers. The way you can reduce this approach value is just by buying larger condensers, and you might be able to get an approach value that's got a 5-degree approach or an 8-degree approach. But that's going to have an incremental savings, and those savings are going to be eaten up by the larger fans and pumps that are going to be associated with those condensers. Now what we can see as far as savings, this is the same type of graph that we just looked at. And the savings with enabling a wet bulb approach is going to correlate to savings opportunities in the summertime and not necessarily in the wintertime, as we saw with reducing the condensing pressure. So in this case here, let's start with our wet bulb temperature, which is our blue line. So this is our average temperature throughout the year. And with our approach is going to be at a fixed amount that's above the wet bulb. And so in the case in the green line, we're going to be at a 25-degree approach. So if we've got a 25-degree approach, as the wet bulb goes up, our condensing temperature and corresponding pressure is going to go up by that same amount. So you can see the difference between the green line and the blue line is pretty fixed during those summer months. But if we can reduce that approach, reduce it down to, say, a 15-degree approach, which is indicative of that red line, then the difference between the red line and the blue line is now 15 degrees, and we're able to bring that down, and we can save compressor power. So the shaded blue area here is the savings that we can achieve by using a lower wet bulb approach value And when combined with reducing our condensing pressure, can really yield good savings throughout the entire year. The next item I want to talk about here is proper sequencing of the condensers. Sequencing can mean two different things. Number one, we do want to sequence the more efficient condensers first if you have a multi-condenser system. More efficient condensers are the ones that have the higher heat rejection with the smaller fan and pump power. But the point I'm bringing out in the slide here is we want to make sure that we're staging the pumps and fans accordingly so that it goes pump first, then fan, then pump, then fan. We don't want a strategy where we do all pumps first and then the fans, or all fans first and then the pumps. The reason being is that the pumps and the fans by themselves don't offer very much heat rejection, and the greatest heat rejection is when they're used in tandem. So as an example here, you can see this excerpt from the Evapco catalog. It was highlighted as with the fan-only control, the arrangement, with the pump-only control, this arrangement only gives you about 10% heat rejection of the rated capacity. So when you've got your condenser, you turn on the pumps, you're only getting about 10% of the capacity of that condenser with the pumps. Fans are the same way. If we're using fans only and not the pumps, you can see the chart below it is the capacity of the condensers right around 10% to 30%, depending on what the ambient dry bulb temperature is. So as the dry bulb temperature goes down to, say, that 0 degree mark, then we're going to be up around 30-35% capacity. As it increases maybe to 35 degrees, then you're only getting about 10 to 15% capacity. So the point is that if you operate just one system or the other, you're not getting nearly the full capacity. But if you bring them on together, then you're getting the full capacity of the condenser. So if you have a multi-condenser system, what we want to be able to do is turn on the first condenser, turn on the pump first, turn on that fan. On the next condenser, turn on that pump, turn on that fan. Next condenser, that pump, that fan. Doing it that way instead of turning on all the pumps will really maximize the heat rejection of those condensers with very minimal horsepower from the fans and the pumps. Here's a good example of the power difference between operating with a pump-pump fan-fan strategy versus a pump-fan-pump fan. So on the chart on the right there, the operating with a pump fan shows you the energy that's being used in that situation. And the blue line is when we're putting all pumps on first. So when we're putting all the pumps on first, you can see that the energy use is actually higher per unit heat rejection as compared to doing it sequentially, as we mentioned. A couple things you want to keep in mind, though, is you do want to keep in mind the water treatment concerns. If you get into a situation when your pumps are cycling, turning on and turning off, there could be some negative consequences with the water treatment and building up scale on the condensers. So that's just something to be mindful of and keep an eye on. And then also you just don't want to be rapidly starting and stopping pumps as well, because of course that's not going to be good for the motors. The next item here is optimizing performance. We want to make sure the condensers are operating in optimal performance at all times, but it's particularly in the summer months. If we can maintain the condensers in prime condition, then that's going to naturally decrease our approach value. So if we have a condenser that's not operating, if it's designed with maybe a 15-degree TD, but it's not operating, it hasn't been maintained very well, there's some issues with it, the water flow isn't that great, it might actually be operating with an 18 or 20-degree TD. So you're paying for that energy penalty with a higher condensing pressure because the condenser hasn't been maintained properly. So some things we want to take a look at is good water distribution, and these are all going to be things that you do on your regular operations and maintenance and preventive maintenance checks. But we want to make sure we have good water distribution. I want to make sure all the nozzles are unplugged and check those on a regular basis. If you've got the older style nozzles that can clog up pretty easily, then we recommend retrofitting to one of these other nozzles you can see here, which are the full flow nozzles, and have a much less chance of clogging up. You want to make sure your pump strainers are clean so you're getting good water circulation through your pumps. Clean out your sump tank annually. Check or spray nozzles we mentioned. Make sure you inspect your eliminators so they're not broken and you don't get any algae growth on those. So you get good airflow, air circulation through there. You want to make sure your fans are operating at their prime as well. Part of that is also staying on top of the fan belts, making sure those are tight. Loose fan belts might result in slippage of 5%, reducing our fan airflow. And then lastly, I want to make sure our purger is functioning. Make sure it's doing the proper number of purges, making sure you do a check on non-condensables to see if it is doing its job, and you're minimizing the non-condensables to maybe anywhere from 0 to 2, 3, 4, 5 pounds in the system. One other nice chart I want to show you here, this is from BAC, which is one of the condenser manufacturers. This just goes to show you what scale on your condenser tubes can do to the performance of a condenser. So in the example you can see right here, and this shows very minimal scale, but in the example here, if you get 1/32 inch of scale on a condenser tube, you can see the reduction in performance of just over 70%. So you might be at 72%. So that's just one reason why you really want to stay on top of your water treatment, because as soon as you get a little bit of scale built up on the condensers, which we all know is going to be very hard to get rid of in the long run, that can severely limit your condensing capacity. And when you limit your condensing capacity, it means your head pressures are going to go up, and you're going to be paying more energy on your compressors. So lastly, in conclusion, we want to make sure we're reducing the condensing pressure to the lowest limit allowable in the system, and that is going to be system dependent. We want to enable wet bulb approach condensing strategy and set our approach values to between 12 degrees to 18 degrees. You want to make sure you're utilizing a pump-fan strategy and optimizing condenser power. And then lastly, maintaining condensers will result in compressor energy savings. So with that, I thank you very much.